Hello everyone, this is Rashmita. Today I would like to solve NCERT solutions for chemistry chapter equilibrium. Let's start. First question, a liquid is in equilibrium with its vapor in a sealed container at a fixed temperature. The volume of container is suddenly increased. First part, what is the initial effect of change on vapor pressure? Second part, how do rates of evaporation and condensation change initially? And third part, what happens when equilibrium is restored finally and what will be the final vapor pressure? Here, we'll actually have a liquid vapor equilibrium. They said fixed temperature. It implies that equilibrium constant for this physical equilibrium remains constant. Whatever the parameters we change, the equilibrium constant never changes because temperature is fixed here. So, on increasing volume, we'll have a large volume available in the container. As liquid vaporizes, the vapor exerts less pressure than initial case because so much volume is available. Volume is increased than before. Volume is increased than before. So the vapor has more volume to exert pressure. So the vapor pressure will be less initially, and the rate of evaporation would be more. As volume is more, surface area available for the liquid to evaporate will be more. Therefore, the rate of evaporation is greater than before. In second effect of in first part, we got that vapor pressure decreases due to more volume available for the vapor to exert pressure. In second case, rate of evaporation will be increasing because of the more surface area than initial case. In second, condensation, and other part is condensation. Condensation is conversion of vapor into liquid. Vapor should convert into liquid because of the availability of large volume. The conversion of vapor to liquid is much difficult. Means rate of condensation will decrease than initial case. Third part, what happens when equilibrium is restored finally and what will be the final pressure? Here, main point of this question is temperature is fixed. As this statement implies the fixed value of equilibrium constants throughout the reaction, whatever the parameters we change, the equilibrium constant always remains constant. So, when the equilibrium is restored, the K is constant, means K initial and K final both are same, equal to K final. Here, this is liquid and this is gas. As this is a gaseous phase reaction, Kp is defined. We can write Kp equals to pressure of vapor. As Kp is fixed, we'll get vapor pressure is also fixed. So, vapor pressure of initial case and vapor pressure of final case remains the same. So, the main point in this question lies with this statement. P is fixed, so equilibrium constants will never change. And vapor pressure decreases because of the increased volume. Rate of evaporation also increases due to the availability of large surface area. And rate of condensation decreases because of the more volume available to the vapor. So, as vapor pressure is less, rate of condensation will also be less. And coming to the next question. What is Kc for the equilibrium when the equilibrium concentrations of each substance? SO2 concentration was given, O2 concentration was given, and SO3 concentration was also given. The reaction is also provided here. So we'll proceed with the next question. In second question, concentration of SO2 is 0.6. Concentration of O2 is 0.82. Concentration of SO3 is 1.9. Also, please always take care of the units. Sometimes we need to convert the units. So I'm mentioning here molar. The given equilibrium reaction is 2SO2, oxidation of sulfur dioxide, 2SO2 plus O2, equilibrium is 2SO3, gives 2SO3, gaseous phase reaction. All reactants and products are gaseous phase. So here we can define Kc as well as Kp. We'll write Kc. As we know, it's product of concentration raised to the powers of their stoichiometric coefficients. Here SO3 stoichiometric coefficient is 2 by here reactants are SO2 and O2. The stoichiometric coefficient of SO2 is 2. And O2 is 1. By substituting the values here, this is 1.9. SO2 concentration is 0.6. Sorry, I forgot the stoichiometric coefficient here. As well as the concentration of O2 is given as 0.82. On calculation, we'll get the Kc value as, wait, let me calculate. I'll inform you. Get the calculation. 12.229, and the units will be molar inverse. As all the units of concentration here is molar, this is molar square, and this will be molar square into molar. This is denominator, so molar inverse will be the units for Kc. So we'll proceed with the next question. Third question. At a certain temperature and total pressure of 10^5 pascals, iodine vapor contains 40% by volume of I atoms. Calculate the Kp for the equilibrium. The given equilibrium reaction is I2 is raised to 2 iodine atoms. Here, we can calculate the partial pressure of I2 as well as I. As they gave 40% of the volume consists I atoms. It implies 60% is I2. As the total pressure is given, we can calculate the partial pressures with the help of mole fractions. mole fraction is of iodine atoms will be number of moles of iodine. Please don't consider the stoichiometric coefficient. Stoichiometric coefficient here helps with the equilibrium concentrations or partial pressures of the reactants or products at a certain time. It has nothing to do with the moles present in the container. So for finding out the moles, we'll use this given information, that is 40% of iodine atoms and 60% of I2. Number of molecules of iodine plus number of molecules of I2 present in the container. As number of molecules is directly proportional to the volume, here we can replace the number of molecules with volume. Volume of iodine by volume of iodine atoms plus volume of I2, volume of iodine atoms. As per the given question, volume of iodine atoms is 40%. So the mole fraction would be 40 by 100. Therefore, the mole fraction is 0.4. Mole fraction of I2 would be, we can either write it in terms of volume or in terms of mole fraction of I. As only two components were present, we can directly write it as 1 minus mole fraction of iodine atoms. This would be 0.6. Here, now we'll find the partial pressures. As per Dalton's law, partial pressure of iodine atoms is total pressure into mole fraction. This is mole fraction of, don't confuse it, this is multiplication. This multiplication. So here total pressure is 10 power 5. Here mole fraction is 0.4 for iodine atoms. Therefore, the pressure would be 4 into 10 power 4 pascals. Whereas partial pressure we'll calculate in the similar way of I2. This total pressure into its mole fraction. Total pressure is 10 power 5 as calculated above. The partial that is mole fraction of I2 is 0.6 in the given container. So we'll have 6 into 10 power 4 pascals. We'll use the Kp relation for this equation. This partial pressure of I, stoichiometric coefficient is 2. So we'll raise the power 2 here. Partial pressure of I2. This would give, by substituting the values, this would give you the answer. 2.67 into 10 to the power of 4. We'll proceed with the next question. AC equilibrium constant expressions for the given reaction. For first part, 2NOCl, 2NO. Yes. Here we need to take care of, while writing the equilibrium constant expressions, you need to take care of the states of the reactants and products. If either of reactant or product is pure liquid or solid, will not include that concentration into the equilibrium constant expression, because that the molar concentration of the pure liquid and as well as pure solid does not depend upon the amount present in the reaction. It is always fixed, so will not include that in equilibrium constant. Here Kc would be molar concentration of NO raised to the power of the stoichiometric coefficient, that is 2. And here Cl2 by here reactant is NOCl. Stoichiometric coefficient is 2. So this is the equilibrium constant for the first part. And we'll go on with the second part. Here the reaction CuNO3 this is solid as well as CuO is also solid. As I mentioned earlier, we'll exclude the concentration of this pure solids as well as pure liquids in the expression of equilibrium constant. This is gas. O2 is also gas. So we'll write Kc only for the gaseous products in this given reaction, because pure solids will not mention in the equilibrium constant expression. So NO2, here stoichiometric coefficient is 4, will raise the concentration to the power 4. Here and O2, no reactant here will be present in the equilibrium constant expression, because here CO and O3 twice is solid. Here O2 is, oh sorry, this is raised with 1. It's just 1. We'll next go to the third part. Here H2O liquid. This is pure liquid. So we'll not include this in the equilibrium expression. So we'll exclude this part. Apart from H2O, other or not pure, they are mixed with water. So we'll write directly the product of concentration of products. Here stoichiometric coefficient of every reactant and product is 1. So we'll not raise to the power any number. So we'll directly write C2H5OH. Here, this is ester. We'll write it by ethyl acetate. Here, take care that pure solids and pure liquids will always be excluded from the equilibrium constant expressions. So we'll go with the fourth part. In the fourth part, only the product FeOH thrice is solid. Thrice is solid. So we'll exclude the concentration of FeOH thrice. Here, Kc will only depend on the concentration of reactants as product is solid. We'll directly write Kc as 1 by Fe plus 3. This is plus 3. Sorry, I forgot to mention that. And here, this is OH minus raised to the power, the stoichiometric coefficient, we'll raise it by 3. And coming to the fifth part, here the printing was not there for the states, but generally F2 occurs as gas, IF5 is also gas, this is gas, this is 2, IF5. Here Kc would be IF5 and stoichiometric coefficient is 2, so we'll raise this to the power and this to the power 5. Here, important note to be taken from this question is that pure solids and pure liquids concentration will not be included in the equilibrium constant expression. That is more important. Even by mistake also, we should not mention that. It will affect the expression of equilibrium constant. So we'll proceed with the next question. Find out the value of Kc for each of the following equilibrium from the value of Kp. First of all, we'll just write a general reaction and we'll reduce the Kp and Kc relation, and we will use that general relation for other reactions given. Let us take small a and stoichiometric coefficient of capital A reactant as small b and capital B reactant as small b, and capital C reactant coefficient is small c, and capital D reaction coefficient is small d. Here Kp product. So this is, remember, this is, I wrote it here mistake. Please correct this as concentration. As I mentioned the concentrations. We'll now write the relation for Kp. This is partial pressure of C to the power C and partial pressure of D to the power D. Now, by using the ideal gas equation, PV equals to nR2. We know that molar concentration, molarity, is number of moles of a substance by volume. So this would be the concentration, molar concentration. So we can write Kp equals, replace the pressure with, here we can write this relation, pressure equals to concentration into R into T. So by replacing that, we can write concentration of C into RT whole power C to concentration of capital D, power is D here, RT power D. Here concentration of A RT power V, concentration of V, with stoichiometric quotient is V. So, concentration terms will be implying Kc here, and RT whole power T plus D minus A plus B. Here, for the given reaction, this relation C plus D minus A plus B is difference of total number of moles of gaseous products minus this is total number of moles of gaseous reactants. We can represent this difference as delta N gaseous products. Therefore, the relation would be Kp equals Kc into RT power delta Mg. So we can substitute we give for first reaction. We gave Kp as 1.8 and mentioned the temperature to be consider the units here as atmosphere, ATM, 1.8 into 10 power minus 2 into temperature minus 500 Kelvin. This is atmosphere. So we'll use the universal gas constant value R in atmosphere liters. It's 0.0 0.0821 atmosphere liters. Mole inverse, Kelvin inverse. Kelvin inverse. So on substituting these values, we can get Kc. Values in the given expression. We'll get Kc for the first part as approximately it will be 4.0 T3 into 10 power minus 4. The second part, similarly, we need to substitute here delta Ng. I forgot to mention the delta Ng value in the first part. We'll go to the first part. Here delta Ng value is 2 plus 1 minus 2. That is 1. Whereas in the second part, delta Ng is also 1, as only CO2 is the gaseous product in the whole reaction. So we'll write delta Ng equals to 1. By substituting those values, we'll get Kc 1.87. Here temperature is different. Please do take care of that. We need to mention the temperature as per the given in question. So fifth question is completed. We'll just proceed to the next question. Sixth question. Here for the following equilibrium case is given as well as temperature is given. Both the forward and reverse reactions in equilibrium are elementary bimolecular reactions. What is Kc dash for the reverse reaction? Here elementary reaction means it takes place in single step. Bimolecular means its molecularity is 2. When two molecules collide to give the desired products. Here elementary reaction and bimolecular is given because we can directly include the products and reactants in the equilibrium constant expression. Or as we need to consider the rate determining step. As per the rate determining step, we need to write the equilibrium constant expression. Here this reaction is itself itself is elementary reaction. So we would directly write the expression for Kc. But they already gave us value. For the reverse reactions, products and reactants would be interchanged. So the equilibrium constant for the reverse reaction, Kc dash, would be the reciprocal for the equilibrium constant Kc in the forward reaction. Therefore, we can directly substitute the value for Kc and get Kc dash 0.3 into 10 power 14. By calculation, we can get this as 1.59 into 10 power minus 15. We'll go for the next question, seventh question. Explain why pure liquids and solids can be ignored while writing the equilibrium constant expression. As I mentioned earlier, the concentration, I'll type it's better. The concentration here, we'll take it as molar concentration. Pure liquid and pure solid is independent of amount of substance present in the reaction. So its molar concentration is always fixed for given temperature, irrespective of its amount present in the container. Is fixed. Therefore, will not include these concentrations in the expression. And we'll proceed with the next question. 6.8. N2 reaction between N2 and O2 takes place as follows. If the reaction moles of N2 is given and 0.933 moles of O2 is placed in a 10 liters reaction vessel and allowed to form N2O at a temperature for which Kc is. Determine the composition of equilibrium mixture. Here, the initial concentrations of reactants were given. So we'll go on with those values. 2N2 plus O2 as well as volume of the container is also mentioned. So we can get the concentrations easily. 2N2O, all are gases. This is 0.482. As the reaction proceeds, here the initial is 0. As reaction we'll consider the case where equilibrium is attained. We'll assume that some amount of, let us say, amount of number of moles of N2 is reactive. Then x by 2 as per the stoichiometry. It's 0.9. For the stoichiometry, x by 2 number of moles of O2 will be reacted. Here x moles of N2O will be formed. In the equilibrium, we can directly write the concentrations as we consider this condition at equilibrium. This is at equilibrium, this condition. So Kc would be concentration of N2O by N2 square. This is concentration, so we'll write volume, number of moles by volume, whole square, by 0.482 minus x whole square, 0.933 minus x by 2. From the value of Kc is very small. So the amount of product formed will be very, very small. This is very, very, very less than 1. So we can say is x is very small. So we can neglect this value of x in denominators. Small. So we can write by neglecting this x as the value of x in denominator, we can directly write above. Please do write the volumes here by 10 because this is not moles, this is concentration. I forgot to mention here. Okay, so we can directly write it as x by 10 whole square by 0.482 by 10 whole square point 933 divided by 10. By substituting Kc value, we'll get x as we get the value of x 6.6 into 10 to the power of minus 21. Question, the composition of equilibrium mixture. So N2O concentration would be 6x by 10. This is sufficient because N2 and O2, x is very small with respect to this initial values. So we can neglect the value of x. We can directly write the initial values of N2 and O2. Only the concentration of N2O here matters because it is newly formed. Even though it's small, we need to mention here. Let's proceed to the ninth question. Nitric oxide reacts with Br2 and gives nitrosyl bromide as per reaction given below. And 0.087 moles of NO and 0.0437 moles of Br2 are mixed in closed container at constant temperature. 0.0518 moles of NOBr is obtained at equilibrium. Calculate the equilibrium amount of NO and Br. So initial values of NO and Br2 were given. This Br2 gives rise to 2 NOBr. So they were mixed. Here, NO value is 0.08287 initially, and Br2 value is 0.0432437. Sorry, and initially it's 0. At equilibrium, this would be 0.087 minus some x. X is the amount reacted. Then this would be 0.0437 minus x by 2. And at equilibrium, this would be x. As per the given question, you have x equals to 0.0518. So, the other, directly we can write the equilibrium amount of NO as 0.087 minus 0.0518 moles. And here Br2 equals to 0.0437 minus 0.0518 divided by 2. These values I'll just calculate and then give you. This is 0.0352. This value is 0.0178 moles. So this is the answer for 9th question. We'll just go with the next question. Temperature at 450 Kelvin, Kp is given as 2 into 10 power 10. For the equilibrium, for the oxidation of sulfur dioxide, what is the Kc at this temperature? As we know, the relation between Kp and Kc, Kp equals to Kc into RT power delta Ng. Here for the oxidation of SO2, delta Ng is 2 minus 1. And therefore, the delta Ng value is -1. Kp is given as 2 into, here units were given as bar and bar inverse. Because delta Ng is -1 here, we'll get per bar. Temperature was mentioned as 450 Kelvin. And as the units of pressure here is bar, we'll use the universal gas constant value as 0.008. Bar liter mole inverse Kelvin inverse. Bar liter mole inverse Kelvin inverse. So substituting these values, we'll get Kc as 1.48 to 10 power 11 molar inverse. Next, we'll go with the 11th question. A sample of HI gas is placed in a flask at a pressure of 0.2 atmosphere. At equilibrium, the partial pressure of HI gas is 0.04 atmosphere. What is the Kp of the given equilibrium? 2 HI gives rise to 2 less I2. 3 are in gaseous form only. So, total pressure equals to initial pressure is 0.2 atm. So, initially this is 0.2 and these two were 0. At equilibrium, it's point. Let us consider pressure decreased due to the reaction of HI is -P. And here some P is formed. Sorry, this is called fragment coefficient is 2. So P by 2 and P by 2 will be formed. Given 0.2 0.2 minus P as 0.04 atm. We'll get P as 0.16. Then pressure of H2 and pressure of I2, both will be P by 2, that is 0.08. Units for ATM. So we better mention that. So KP is given as partial pressure of H2 to partial pressure of I2 divided total division divided by total pressure of partial pressure of HI whole square. Where this is stored. Partial pressure of H2 is 0.08. This is 2 times, so we'll directly do it as square. Partial pressure of HI is given as 0.04 in the question. So we'll directly mention that square. On calculation, you get it as 4. We'll go with next question, that is 12. Mixture of 1.57 moles of N2, 1.92 moles of H2, and 8.13 moles of NH3 is introduced into a 20 liters reaction vessel, 500 Kelvin. At this temperature, the equilibrium constant Kc for the reaction is. If the reaction mixture at equilibrium, if not, what is the direction of its reaction? Here, when all products and reactants were introduced into the vessel, we need to check for the reaction quotient. Reaction quotient Q expression is similar to that of equilibrium constant expression, but the difference is that concentrations for the equilibrium constant will be the concentrations that occur at the equilibrium. But for the reaction quotient, at any time that where we want to check. Here, we want to check at initial condition whether to determine the direction in which the reaction proceeds. For this, the reaction quotient Q will be, expression would be same as Kc. So, NH3 square into H2 cube. So, NH3 square is 8.13 moles were given, but we need concentration. Please don't forget the volume. This is 20. Divided by N2 is 1.57 moles. Divided by 20. This is H2 is 1.92 moles and volume is 20. Stoichiometric coefficient is 3. So we'll raise it to the power 3. In calculation, we get Q as 2.4 into 10 cube. Observe the Kc value. It's just 1.7 into 10 square. So reaction quotient is greater than Kc. That means products are in excess quantity than reactants. So the reaction would proceed backwards. Remember these conditions. If reaction quotient is greater than equilibrium constants, products are higher. So the reaction would proceed backward. If Q is less than Kc, products were low, reactants were high, the reaction would proceed forward. Another condition, when reaction quotient is equals to K, it means the given concentrations are equilibrium concentration, so reaction is at equilibrium. I'll go with the next question, that is 13th question. The equilibrium constant expression for gas reaction, write balanced chemical equation corresponding to this expression. Here carefully observe that Kc is NH3 power 4 and O2 power 5 and NO power 4 and H2O power 6. So therefore the reaction for this would be NH3 and O2 were products, NO and H2 are reactants. But here we need to observe that the powers raised will be the stoichiometric coefficient only. So first of all, we'll write the skeleton of this reaction, then we'll mention the stoichiometric coefficients here. Reactants and products, this is NH3 plus O2. Here observe that if H2O is liquid here, will not include this H2O in the equilibrium constant expression. But H2O is included here, so this must be in vapor phase. And as they already mentioned, it's a gas reaction. So all reactants and products would be gas. Carefully remember that if H2O is liquid, then it won't be appeared in the expression. Now, we'll write the stoichiometric coefficients as per the powers to their respective reactants or products. Here, NH3 power is 4, so the reaction coefficient, stoichiometric coefficient is 4. And here, power is 5 for O2. We'll write the stoichiometric coefficient as 5. Here, the stoichiometric coefficient is 4. And for H2O, it would be 6. You need to carefully consider the case for H2O. If it's vapor, then it will appear in the reaction equilibrium constant expression, or else it won't be appearing in the expression. Next, we'll go on with the 14th question. 14th question. 1 mole of H2 and 1 mole of CO are taken in 10 liters vessel and heated to 725 Kelvin. At equilibrium, 40% of water by mass reacts with CO according to the equation. Calculate the equilibrium constant for the reaction. Here, H2O, all are gases. So H2O is also gas here. So its concentration also matters while writing the expression. So please take care of that. H2 general mistakes will be done while considering the pure liquids and pure solids concentrations. So this is the reaction. So for the further calculation, this is 1 mole, but for 10-liter vessel, so 0.1 molar concentration, 0.1. This is also 0.1. And H2 is 0 initially. Finally, 40% of water is reacted. Initially, 1 mole, out of which 40% is reacted. So 0.4 is reacted, but as per the concentration, 0.1 minus 0.04 is reacted. 0.04 is reacted. Based on this stoichiometry, we can directly write as 0.1 minus 0.04 is reacted. Left over at equilibrium for CO as well. Your point is there. Here we'll get 0.04. This is also 0.04. Equilibrium constant would be Kc is concentration of H2 into CO2 by H2O. Here H2O is gas. That's the reason I'm mentioning it in the expression. And CO. Substitute the above values. We'll get the answer as 0.4. Go on with the next question. 15th question. At 700 Kelvin, equilibrium constant for the reaction is 54.8. If 0.5 moles per liter of HI gas is present at equilibrium, what are the concentrations of H2 and I2 gas? Assuming that we initially started with HI and allowed it to reach equilibrium. Means basically, according to this equation we started backwards. Means from HI, H2 plus I2 gives rise to 2HI. Equilibrium constant Kc is given as 54.8. Temperature is mentioned as 700 kelvins. Here, initial HI is equals to 0.5. Let us consider some X is some C concentration is getting reacted. So, concentration of H2 form will be C by 2 and concentration of I2 form will be C by 2. From the Kc expression, you can write Kc is for that forward reaction. So, we'll directly write that forward reaction divided by H2 into I2. So, Kc is 54.8 8. If we equate, you'll get HI is 0.4 minus some capital C divided by capital C by 2 into capital C by 2. On calculation, we'll get C as approximately 0.068. Here, what did they ask in the question? Equilibrium constant is given. Concentrations of H2 and I2. Concentrations of H2 and I2 would be capital C by 2. That's it. Take 1 minute. Here we'll get the capital C by 2 value as 0.068. Therefore, the concentrations of H2 and I2 will be 0.068 only. Then we'll proceed to the next question. 16th question. What is the equilibrium concentration of each of the substances in the equilibrium when the initial concentration of ICF is given? Sorry for the confusion led here. This is not 0.5 minus C because carefully observe here. As per the given question, 0.5 is at equilibrium. So it's not required to take into the concentration of the amount reacted in the reaction. So we'll eliminate these terms. C by 2 is also not required here. Sorry for that. Remove this as well. This is C is enough. Here also C is enough. In the calculation, 0.5 minus C is not at all required. So I'm removing that. This is C. We considered the equilibrium concentration of H2 and I2 to be C. So we'll directly mention that. We'll get the value as 0.068. Sorry for that confusion here. They gave concentration of HI as 0.5 moles per liter at equilibrium itself. It's not the initial value, so it's not required to take the amount reacted. We can directly include this 0.5 in the equilibrium constant expression. So we can directly write that. Next, we'll proceed with the 16th question. What is the equilibrium concentration of each of the substances in the equilibrium when the initial concentration of ICL? Here, the difference between the previous question and here is that the concentration mentioned is not at equilibrium. It is at initial condition. So, we'll write the concentrations according to that. I'll clearly mention at what time the concentration is. Initially, it's 0.78 as per the given question. It's 0.78 and these two were 0 as the reaction did not occur initially. After occurrence of the reaction at equilibrium condition, let us consider that some C concentration was reacted. So C by 2 concentration of I2 will be formed here. Here also, as per the stoichiometry, only I am writing the C and C by 2. If we take this as 2C, these two will become C and C. Given Kc was given, so we can directly write this Kc equals to concentration of I2, that is C/2. Kc is not that small, so we can't neglect the C from the denominator. So we'll directly need to solve the quadratic expression obtained here. Minus. Upon calculation, we'll just observe that C/2 will be given as 0.167. That is the concentration of I2 and Cl2 is 0.167. For equilibrium concentration of ICl, we'll just directly subtract that 0.78 minus C. That is 2 times of 0.167. On calculation for this, we'll get the value as 0.446 units molar. So this question was completed. We'll go for the next question, 17. Ap is given as 0.04 atmospheres. What is the equilibrium concentration of C2H6 when it's placed in a flask of 4 atmosphere pressure and allowed to come to equilibrium? That is, initial pressure of C2H6 was given. Similar to that of concentrations, we can subtract the pressure as well. As the reaction proceeds, the pressure of reactant goes on decreasing and pressure of products goes on increasing, and both reaches a constant value at equilibrium. Although the equilibrium phenomena is dynamic, that is, the reactions and products all continuously convert back into each other, but the concentrations of those reactants and products remains constant at equilibrium. All physical properties of the reactants and products remains constant, that is, pressure, concentration, color, and other physical states also remains constant at the equilibrium. This is 4 ATM. We'll just consider minus P. Here, stoichiometry coefficient is 1, so we'll directly write it as P. For the given Kp, 0.04 is equals to P square, that is P into P by 4 minus. On solving, we'll get the value of P as 0.38. So, they asked about the equilibrium concentration of C2H6. That is pressure, equilibrium pressure at C2H6 is 4 minus 0.38. Your point is there. Please do take note of that. Answer is 3.62 atmospheres. This is 18 as the given pressure is in units of radian. Then we'll proceed with the next question. Ethyl acetate is formed by the reaction between ethanol and acetic acid, and the equilibrium is represented as CH3COOH plus C2H5OH, CH3COO C2H5 plus H2O. Write the concentration ratio QC for this reaction. Observe the bracket. Note water is not in excess and is not a solvent in this reaction. Here, water is not a pure liquid. So, we'll consider this in the equilibrium constant expression. So we should not neglect the concentration of water. As a result, we need to include the concentration of water. For the first one, we'll write the QC. QC is reaction quotient, ester water, right? Acetic acid. This is the expression for QC. QC is nothing but concentrations at different times. Apart from the equilibrium, if it is equilibrium, QC is QC. We'll write it as equilibrium constant. And second part, if one starts with 1 mole of acetic acid and 0.18 mole of ethanol, there is 0.17 mole of ethyl acetate in the final equilibrium mixture. So, initial is 1 for acetic acid, 0.18 for ethanol. Ethyl acetate is 0 as well as water is also 0. Let us consider, after proceeding to equilibrium, consider X is reacted. 0.18 as per the stoichiometry, it will also react in X amount. And this is produced in the X amount. Water is also produced in X amount. And the question they gave, at equilibrium, the X, that is, the moles of ethyl acetate is 0.171. Equilibrium concentration would be, equilibrium constant would be Kc into equals to X into X. This is X divided by 1 minus X point 1. So substitute the values. After substituting, you will get the equilibrium constant value as 3. Observe here, there are no units for Kc as they get cancelled in numerator and denominator. Okay. Then third part, starting with 0.45 ml of ethanol, 1 mole of acetic acid and maintaining it at 293 Kelvin, 0.214 mole of ethyl acetate is found after some has equilibrium been reached. Here, we don't know whether it's equilibrium condition or not. We're just taking the concentration. They mentioned the concentrations at some random time. Carefully observe that this is not the equilibrium time. The reaction did not achieve the equilibrium or not. We had to verify that with the help of reaction quotient. One mole acetic acid, 0.5 and this is 0 initially. This is also 0 as well. This would be, consider Y amount is taken, is reacted as per the stoichiometry. This is 0.5 minus Y. This is Y. This is also Y. As per the question, Y is given as 0.214 at certain time. We don't know whether it's equilibrium or not. We need to confirm that using the reaction quotient. We'll find out Q. Y square divided by 1 minus y into 0.5 minus y. Substitute the y value. We'll get q as 0.20307. This is a very less value than Kc obtained in the, we need to find a minute from the from the second part, we got Kc. Q is less than Kc, so equilibrium is not achieved yet. I am taking the same value as second part because only temperature affects the value of Kc, not the concentrations of reactants or products. So the same Kc will be there for third part as well because the reaction is same for second and third part. So the question was completed. We'll go for the 19th question. A sample of pure PCl5 was introduced into an evacuated vessel at 473 Kelvin. After equilibrium was attained, concentration of PCl5 was found to be 0.5 into 10 power minus 1 moles per liter. If value of Kc is 8.3 into 10 power minus 2, what are concentrations of PCl3 and PCl2 at equilibrium? Here, the equilibrium concentration of PCl5 is given. We need to find out the equilibrium concentrations for PCl3 and Cl2. No need to worry because both concentration of PCl3 and PCl3 as well as Cl2 will be same. As only PCl5 was introduced into the vessel initially, we'll just directly take the value at equilibrium itself, 0.05, that is 0.5 into 10 power minus 1. We'll take this as x. This is also as x. From Kc equals to x square by 0.05. From this, we'll obtain x as 0.0204. Directly, the equilibrium concentration of PCl3 and Cl2 would be 0.0204 moles per liter, that is molar. Go on with the next question. One of the reactions that takes place in producing steel from iron ore is the reduction of ferrous oxide, that is iron to oxide, by carbon monoxide to give iron metal and CO2. Kp is given. What are the equilibrium partial pressures of CO and CO2 at 1050 Kelvin? If the initial partial pressures. Here, observe carefully. The initial partial pressures of reactant as well as product both were given. So, we need to find out the Qp value. If based on that value, we need to determine whether the reaction is going in forward direction or backward direction. To find that, we'll just substitute the initial values in the QC expression and writing the reaction. Of solid. Carefully observe that FeO and FeS are pure solids. These two terms were not included in the equilibrium constant expression. So no need to worry about those two concentrations. So we'll directly write Kp as pressure of CO2 divided by pressure of CO. Okay. I'll substitute the initial. This is not, this is Kp expression. These pressures would be at equilibrium. Now we'll write the expression for Qp. Qp is also same, but pressures will be at, here we'll consider the initial pressures and we'll calculate. So pressure would be 0.8 divided by 1.4. Here we'll obtain Qp as value. We'll get 0.5 7 1. Kp is less than Qp. That is, products are in greater concentration, so reaction would proceed backward. So this is backward sign. Therefore, carefully observe that it's moving backward. So CO2 pressure would decrease. I'm not writing the other terms because they were not included in the equilibrium concentration. I'm concerned with only these two terms. Here, this is 0.80, consider it as minus P. This is 1.4. Always carefully read the question whether the given concentration of pressure is at equilibrium or any initial conditions. If both reactant and product concentrations were mentioned, then you need to check for QC and KC. Whether KC is greater, then the reaction would proceed further. If whether QC is greater, then the reaction would proceed backwards. You need to carefully observe those reactions. By writing the expression of Kp, partial pressure of CO2 by partial pressure of CO, we can directly write it as 0.8 minus P by 1.4 plus P. This will get partial pressure, that is this P, as 0.339 atm. Then you can directly minus it to get the individual partial pressures. Partial pressure of CO2 would be 0.8 minus 0.339. This value is 0.461. Partial pressure of CO would be 1.4 plus 0.339. So the value for CO would be 1.739. Okay. We are done with the question. Hello, sir. Hello. Hello, sir. Hello. Sir, am I audible to you? Hello. 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 So then we'll proceed with another question. 21st question. Equilibrium constant Kc for the reaction is given. At a particular time, the analysis shows that composition of reaction mixture is 3, 2, and 0.5. Is the reaction at equilibrium? If not, in which direction does the reaction? Here it simply asks, here we can simply use the relation between Q and K. Here we can directly calculate the Q as 0.5, that is NH3 concentration whole square by 3 to 2 whole cube. Then we'll obtain the value 0.0104. This is less than Q. Q is less than K. So the reaction will proceed further. Next question. 22nd question. We'll just finish this question. Initial pure BRCl is present at concentration. Ac was given 3.3 into 10 power minus 3. What is molar concentration in the mixture at equilibrium? Okay. Kc is given, BRCl equilibrium initial concentration was given. This is 3.3 into 10 power minus 3. We'll just consider x minus 6. If x amount is reacted as per the stoichiometry by 2 and x by 2. The expression of Kc can directly write x by 2 whole square 3.3 into 10 power minus 3. This will get x, don't worry, this is x by 2. I'm writing the x by 2 value. It's 1.5 into 10 power minus 3. So BRCl concentration would be 3.3 into 10 power minus 3 minus x, that is 3 into 10 power minus 3. Directly write it as 0.3 into 10 power minus 3. Concentration of Br2 and Cl2 are 1.5 into 10 power minus 3. I'll continue with the other questions in the next session. Thank you.